A ladder of length 3 meter and mass 20 kilogram leans against a smooth vertical wall so that the angle between the wall and the ladder is 30 degrees. What are the magnitude of the normal force at the contact point on the wall, Fw, and at the contact point on the ground, Fg? So this is the ladder which is leaning on the wall, and the ladder makes an angle of 30 degrees. What is the normal force which is acting on the ladder from this wall and the normal force from the ground? To determine Fw and Fg, we are going to use the concept of equilibrium. Directly we can see that this is the center of mass of the ladder, we can say. So mass times gravity of the ladder is acting downward. So since the length of the ladder is 3 meter, up to this point is half, or 1.5 meter is the center of mass of the ladder. Then from the concept of equilibrium, we have two conditions of equilibrium. The first one says that the sum of all the force acting on the objects must be 0, and the second condition is the sum of all the torques acting on the object is also 0. Then from the first condition of equilibrium, the sum of the force acting on the object is 0, means we have 4 forces acting on the object. One is normal force from the wall, the other is weight of the ladder itself, and the normal force from the ground, and the frictional force which preventing the ladder from sliding. So if we add all the vertical and horizontal forces, then from the vertical force, that means the sum of all forces acting along the y is equal to 0. This implies that mg is acting downward and fg is upward. So we can say fg minus mg is equal to 0. This means that Fg is equals to mass times gravity. So we can simply substitute the values of mass of the ladder is 20 kilogram times acceleration due to gravity, which is 10 meter per second square. So Fg is directly equal to 200 Newton. Then from the sum of the horizontal forces, Fx, which is equal to 0, this means that F horizontal means Fw is acting to the right along the positive x-axis and frictional forces to the left. So we can write that Fw minus F is equal to 0 directly. Then Fw is equals to the frictional forces. So we don't know the values of F, so we need to calculate the values of F, or the values of Fw, by using the concepts of the torque. So to find Fw, just we use the concepts of the torque is the second condition of equilibrium, which says the sum of all the torque acting on the ladder is 0. So take the base of the ladder, this is the base of the ladder, as the hinge or the pivot point, and we use Fw and mg to rotate either clockwise and counterclockwise, and the sum of all that torques is 0. So then from this we can see that if this is the Fw, and we can resolve Fw into two components. One component is which is along the ladder, and the other component is which is perpendicular to the ladder. So this is Fw, which is perpendicular to the ladder, and this one is the component along the ladder. And mg also can be resolved into one component, that is mg, which is perpendicular to the ladder, and the other component is mg, which is parallel along the ladder. So just if we take this is the length of the ladder, and up to mg we have L over 2, that means center of mass of the ladder is at the center of this ladder, and the total length of the ladder is 3 meters, so this is 1.5 meter directly. So then the torque produced by the Fw perpendicular to the ladder and the mg perpendicular to the ladder is directly 0. So mg perpendicular means mg times sine of 30 degree, and this is this value, and Fw perpendicular to the ladder means if this angle is 30 degree, we know directly this is 60 degree, so this is directly sine of 60 degree, or we can use this is Fw sine of 60 degree, or which is equals to FW the cos of 30 degree. We can use like this because cos of 30 degree is equals to sine of 60 degree. They are equal. So from the second condition of equilibrium, which says the sum of all the torque acting on the ladder is 0, then we can see that mg sine of 30 degree is making the counterclockwise torques, and FW cos of 30 degree or FW sine of 60 degree making the clockwise torques. So we subtract clockwise torques from the counterclockwise. The counterclockwise torque is mg sine of 30 degree times length of the ladder over 2, because mg is acting at the half of the length of the ladder, minus the clockwise term torques are FW cos of 30 degree times L, it acting along all the lengths of the ladder. So this is directly equal to 0. So if we rearrange this equation, mg sine of 30 degree times L over 2 is equals to FW cos of 30 degree times L. So L cancel from both sides, and directly we see that FW is equals to mg over 2 times sine of 30 degree divided by cos of 30 degree. Or directly we can say it is mg over 2 tan of 30 degree. So directly if we substitute the value, mass of the ladder is 20 kilogram times g is 10 meter per second square divided by 2 times tan of 30 degree is directly 0.5773, and it continues, so we can round off it or simplify it. Then 20 by 2 is 10, directly we have 10 times 10 is 100 times 0.573 is equal to 57.7 Newton force. In the first case, Fg is equal to 200 Newton, and now we have calculated that Fw is equals to 57.7 Newton. So the correct answer is on alternative C. Object of mass 3 kg is hanged by 3 ropes. Rope 1, 2, and this is the third one. Then if the system is in equilibrium, what will be the tension T1 and T2? Where theta 1 is 53, an angle which rope 1 make with this horizontal, and the theta 2 is 37 degree. It is the famous equilibrium problem. Then we can solve it easily by using the concept of equilibrium. For the first condition of equilibrium, which says the sum of all the forces acting on this system is 0. Like this is the point at which this mass is acting, and mg of the object is directly downward, and the tension T2 is acting like this, and the tension T1 is acting like this. So then if we draw the free body diagram along x and y axis directly, we can see that this is the x axis, and this one is directly theta 2, and this is equals to theta 1, and this one is, we can say, as a y axis. So then the sum of all the forces acting along the x axis is equal to 0, and the sum of all the forces acting along the y axis is also there. So before doing this, we can resolve this T1 and T2 into x and y components. That means if we resolve for T1, the component of T1 which is acting along the x-axis is directly we can say T1 times cos of theta 1, and the component of T2 which is acting along the x-axis is T2 times cos of theta 2 along this direction, and the component of T1 which is acting along y-axis is T1 sine of theta 1, and the component of the T2 which is acting along the y-axis is also T2 times sine of theta 2. So the components of T1 and the T2 acting along the y-axis are parallel, they are both upward, and mg is downward. So the vertical components of the forces directly given by the sum of the all the Fy is equals to 0, means that we can say T1 sine theta 1 plus T2 sine theta 2 minus mg is equals to 0. Then if we rearrange this equation, T1 sine of theta 1 plus T2 sine of theta 2 is equals to mg as a first equation. And the second equation is from the sum of the forces acting along the x-axis from the components of the force acting on the x-axis, which the sum is equal to 0. Then we can see that T2 cos theta 2 minus T1 cos theta 1 is equal to 0. Then if we rearrange, it means that T2 cos theta 2 is equals to T1 cos of theta 1. This is equation 2. Then from the two equations, we can see that from equation 1, T1 sine theta 1 plus T2 sine theta 2 is equals to mg, and T2 cos theta 2 is equals to T1 cos theta 1. Since theta 1 is 53 degree and theta 2 is 37 degree, if we substitute in this equation, T1 times sine of 53 plus T2 times sine of 37 is equals to, so mg means simply m is 3 kilogram and g is 10 meter per second square, so directly we can get 30 Newton. And from this equation directly we can see that T1 times sine of 37 is 0.6, so this is directly sine of 53 is 0.8, so we have 0.8 T1 plus sine of 37 is 0.6, so this is 0.6 T2 is equals to 30 Newton. This is from the first equation. So from the second equation, we know that T2 cos of theta 2 means since theta 2 is 37 degree, cos of 37 is 0.8. So we have 0.8 T2 is equals to 0.6 T1. This is from the second equation. This is the first equation. Then we rearrange these two equations and solve for T1 and T2. So from the first equation, we know 0.8 T1 plus 0.6 T2 is equal to 30 Newton. And from the second equation, 0.8 T2 is equal to 0.6 T1. So then from this equation, just I can find T2 is equals to 0.6 over 0.8 T1, and then we can substitute the place of T2 in this equation and solve for T1. Then by substituting the values of T2 into the first equation and solve for T1, directly we can get that T1 is equals to 24 Newton, and from this equation, if we substitute the values of T1 here, we get T2 is equals to 18 Newton. So T1 is 24 Newton and T2 is 18 Newton. The alternative which combine these two values is on alternative D. The ladder, which weighs 200 Newton, is leaning on the wall and it makes an angle of 53 degrees with the horizontal or with the ground. Then a firefighter of 600 Newton is at a 6 meter from the ground, and the length of the ladder is 10 meter, and the firefighter is 6 meter above the ground, and the center of mass of the ladder is at the center of the ladder. We assume like this. So this is at a 5 meter, firefighter is standing at a 6 meter above the ground. If the ladder is about to slide, that means if it is in a limiting equilibrium, what will be the coefficient of friction between the ladder and the ground? Since the frictional force preventing the ladders from sliding, then the coefficient of that friction is how much when the ladder is about to slide. That means reaches the maximum static frictions. And then we can resolve this the weight of the ladder in two components. One is lying along the ladder itself and the other is perpendicular to the ladder, which is causing the torque. And also the weight of the firefighter, 600 Newton, can be resolved the perpendicular and the parallel component. And the normal force from the wall also resolved into two components, the component which is perpendicular to the ladders. So by using this information and apply the concepts of equilibrium, we can find the coefficient of friction, because the coefficient of friction is frictional force is given by the coefficient of friction times normal force from this ground. So therefore the mu, coefficient of friction, is equal to the frictional force divided by the normal force from the ground. So before, we don't know the values of the friction and we don't know the values of the normal force from the ground. So we determine these two forces first. Then from the concepts of equilibrium, that means the first condition of equilibrium, the sum of all force acting on the object is equal to 0. This means that Fg is upward, that is normal force from the ground, minus the weight of the ladder, minus weight of the firefighter, which is equal to 0. Then directly from this equation we can see that the normal force from the ground is equals to weight of the ladder plus weight of the firefighter, which is 600 plus 200, which is equals to 800 Newton. So this is the values of Fg. The sum of the forces along the horizontal is also 0. This means that the normal force from the wall minus the frictional force is equal to 0, since they are opposite. Frictional force is acting to this left. So that means that the normal force from the wall is equals to the frictional forces, but we don't know the Fw and the frictional force both. So to determine this, we use the second condition of equilibrium, which says that the sum of all the torque acting on the ladder is 0. So if we take the base of the ladder as the hinge, and Fw sin theta is causing the torques along the clockwise direction, and the components of the weight of the firefighter and the components of the weight of the ladders are causing the counterclockwise torques. So the sum of all the torques are equal to 0. So this is the weight of the firefighter, component of weight of the firefighter at 6 meters, and this is the components of the weight of the ladder, which is at 5 meters, minus this is the components of the normal force from the wall. So these sums are simply equal to 0. Then if we add all these two numbers and rearrange it, we get directly 2760 Newton meter, which is equals to 8 meter times Fw. Then Fw is equals to 2760 Newton meter divided by 8 meter. Meter is cancelled by a meter, and we get directly 345 Newton. So this is the Fw. Since Fw, normal force from the wall, and the frictional force are equal, so we can write that the frictional force, which is equals to the normal force from the wall, is 345 Newton. Then from our previous equation, the coefficient of friction is equals to the frictional force divided by the normal force from the ground. So then mu is equals to the frictional force is 345 Newton divided by the normal force from the ground is, we have calculated earlier, it is 800 Newton. So Newton cancelled by Newton, and this become 0.4313. The correct answer is on alternative B. Which one of the following statement is not correct about a particle that is in equilibrium? Alternative A says that it can have a velocity different from 0. Yes, this is true, because a body in equilibrium can have a velocity, but that velocity must be a uniform. That means constant velocity. The object must not be accelerating. That is in a dynamic equilibrium. Alternative B says that its velocity can be equal to 0. That means velocity of the object can be 0. This is when the object is at rest, that is static equilibrium. It is still true. Alternative C says that it can be under the action of more than one forces. To talk about the equilibrium of the object is that object must be under the action of more than one forces. That means if only single force is acting on the object, we cannot talk about the equilibrium, because that single forces make the object to accelerate. So if more than one force is acting on the object and the sum of all that forces are zero, the object is still in equilibrium, and this is still true. Alternative D says that it can have an acceleration different from zero. So this statement is completely wrong. That means a body in equilibrium cannot have an acceleration. That is, either it has a uniform motion in a uniform motion or constant velocity, or its velocity can be zero. So if the both cases are fulfilled, the sum of all the forces acting on the object is equal to zero. So the sum of the force is zero means the acceleration of the object is also zero. So this is not correct. So the alternative which is not correct about the equilibrium of the particle is D. A uniform bar of length 2 meters and the mass 30 kg is supported by two light strings, and T1 and T2 are the tension in both strings, and the weight W, which is 700 Newton, is hanging at D is equals to 0.5 meter from the side of tension 1. What will be the tension T1 and T2 if the system is in equilibrium or the bar is in equilibrium? So here, to find the values of T1 and T2, we can apply the first condition of equilibrium, which says that the sum of all the forces acting on the bar is equals to zero. This means that T1 is upward plus T2 is also upward minus W minus weight of the bar is equals to zero. So this indicates that directly T1 plus T2 is equals to the W, which is hanging on the bar, plus the weight of the bar itself, which is mg. So directly we can see that T1 plus T2 is equals to 700 Newton plus m times g, which is 30 times 10, which is 300, and T1 plus T2 is equals to 1000 Newton. So take this as equation 1. So from the second condition of equilibrium, the sum of all the torques acting on the bar is also zero. Then now I take the center of mass or the center of the bar as the hinge. Take this point is hinge or pivot point. Then W and T2 is making the counterclockwise torques, and T1 is making or forming the clockwise torque. So if this is the point of rotation or the pivot point is, so I can find the all torques and equate with zero. The counterclockwise torques are created with or formed with tension T2 and the weight which is hanging from the bar W. So I can say that T2 times 1 meter, because the rod is 2 meter and the center up to the T2 is so 1 meter. This is the W weight which is hanging from the bar, and the D is 0.5 meter, and from this point up to the center is 1 meter. Then D is at there 0.5 means here from this side 0.5, also from this side is 0.5. So W times 0.5 meter minus the clockwise torque is at T1 times 1 meter, which is equals to 0. Then rearrange this equation. So we can say T2 times 1 meter means simply it is T2 plus W times 0.5 is W is 700 and times 0.5 means 350 Newton meter minus T1 times 1 meter is T1 meter, which is equal to 0. So if I rearrange this equation and solve for T1, just I can say T1 is equals to T2 plus 350 Newton meter. So take this as equation 2. So we have two equations. T1 plus T2 is 1000 Newton and T1 is equals to T2 plus 350 Newton. Then from this equation I can find T2. T2 is equals to 1000 Newton minus T1, and then if I substitute this value into the second equation, I get that T1 is equals to 1000 Newton minus T1 plus 350 Newton meter. So if I transfer T1 to this side, I have twice of T1 is equals to this number added together as 1350 Newton meter. So T1 is this number divided by 2, that is 1350 Newton meter divided by 2 is equals to, by the way, here T1 is times meter. All the places of T we have meter and meters, so that meters divided by, I divide 2 by 2 meter, so then this meter cancel, and if I divide the number together I get 675 Newton is left there. So the place of T I have a meter, meter and meter because I multiplied it by 1 meter. Then from the equation 1, just we have substituted that T2 is equals to 1000 Newton minus T1, which is 1000 Newton minus T1 is 675 Newton, and directly we can get that T2 is 325 Newton. So we can write as T1 is equals to 675 Newton and T2 is equals to 325 Newton. But the sum of them is altogether it must give 1000. So the correct answer which combine these two values is on alternative A.